Nu, au scăpat toate. Asta era important, e ok. Hai să te cablez eu până...
Okay. Testing, testing. Okay, we're good. Hello and welcome everyone. My name is Adrian. Because this is the first time I present in front of a live audience this size, I'm going to start with some things about me. I'm a DevOps engineer. I really enjoy traveling and attending international parties, being a big fan of festivals. I used to be an amateur gamer as well, spending a lot of time in battle royale games. About technological preferences, I can say that I'm a big fan of the DevOps discipline, particularly being fond of cloud computing. I'm in Endava for about over a year now, from a total of over 10 in the IT industry. I've worked in banking projects, currently in telecom and data transmission project, and in the past in media and big data projects. Today, I'll speak about one of the tools encountered in the DevOps discipline, Terraform. Has anyone heard about it so far? Okay, great. Before we can understand its utility, especially in Google Cloud, we must first get a grip on cloud computing, infrastructure as code, and the several tools that exist along with their purpose in administering the modern infrastructure. I'll stop and explain the reason why I believe Terraform is one of the best solutions for the job, and I'll end the presentation by live demoing a concrete example of deployment, where I'll show the agility with which the resources are created, configured, and when no longer needed, removed. Disclaimer, no yaks were harmed during the making of this presentation. Let's all refresh our memory and take a look on how software is delivered in a traditional IT model. Let's take, for example, a company that wants to deliver a new app. The business team presents the functionalities and the needs. Then the business analyst team analyzes them and brings up a set of high-level technical requirements. The software architects create the blueprint and the steps which will be followed for launching it. This includes requirements related to the infrastructure components, such as the number, the type, specifications of the backend, frontend, databases, servers, etc. Taking into consideration that we're in the traditional IT model, this means that everything should happen on the on-premise servers of the company. So we'll have to make do with what we have. If more resources are needed, they will be purchased by the acquisitions team. This team will forward the requirements to the suppliers, which automatically implies a delivery period, which can take up to months. Once the components have arrived, the on-site engineering team will be responsible for mounting and stacking the racks. The sysadmins will configure them to be accessible via the network. The storage and backup admins will configure the capacity and backup schedule. Finally, after this new system is brought to standards, it can be handed over to the applications team, who will start working on the software itself. This model, which is still quite used a lot, even though the recent pandemic helped diminish the percentage, has a lot of downsides. Mainly, it can take anywhere from a few days to a few months just delivering the hardware and setting it up. Also, vertical scale is impossible to accomplish in a short time. The costs for such investments can be quite high. Even though some processes can be automated, placing the equipment, cable management, powering must be manually done and is generally a tediously long process. Also, by engaging so many teams and making them interdependent, chances for human errors exponentially increase. These things usually lead to differences between environments. Another major disadvantage of this model is the underutilization of resources. Generally, companies tend to consider cases where more is better, which means they consider the peak utilization. That means when we have vacation days or low traffic, the company wastes money, and I'm not even considering the time devaluation of hardware technology. In the last approximate 10 years, many companies began migrating to the large cloud providers such as Google, Amazon, or Microsoft. By doing so, they've massively reduced the time with infrastructure and servers. Why? Simply because the cloud model, we don't have to invest or personally maintain the hardware equipment. Data centers are independently taken care of by said providers. For us, this means that when we need more computing power, a virtual machine can be launched in several minutes. While in the traditional model, in the best cases, several weeks. Also, in the cloud model, we reduce a lot of costs with buildings, logistics, personnel, power, other utilities, which brings a lot of great advantage to startups and low capital developers. In the cloud model, there's also a lot of support for the APIs, which opens up a whole new world for automation and error elimination. Finally, through scalability and elasticity, we can also get rid of resource underutilization. While this model is definitely better and faster than the traditional one, using a cloud provider's console for configuring and launching resources is not always the best idea. Don't get me wrong, there's nothing wrong with it. However, this approach is generally good when you have a limited number of resources. Let's say 10 if we're being persistent and grindy. In a large organization with immutable infrastructure and scalable elastic cloud, this approach is not feasible. As a small side note, I can say from a personal experience that about 8 years ago, when I was in charge of migrating some of the servers of the company which I used to work for, things began to be difficult to remember and keeping track of. It was a complete headache when I needed to give or take away access for resources and departments. Keeping a log of users, roles, types of machines, zones, access controls lists was really difficult. Back to the main idea. Once provisioned, the cloud resources will have to be double-checked by several teams. This thing leads to an increase in delivery time and the chances of human errors appearing. We might have, again, inconsistencies between environments. These being said and taken into consideration, several to most companies began working on different solutions for solving these issues and making things run more smoothly. Some organizations used simple shell scripts, some used complex programming languages such as Perl, Python, Ruby, or why not PowerShell. Everyone was trying to solve the same problems to deploying infrastructure in an automated way. Everyone was trying to make these deployments go faster and more consistent throughout the environments by using the APIs different cloud platforms were offering. These scripts have now evolved into something that we call infrastructure as code. Using infrastructure as code, we can take care of any infrastructure component. These can be databases, networks, storage space, or we can even configure applications. In a shell script, the code is quite difficult to write and it requires a set of good competences to adapt it to different situations. So, its portability is limited and it can't really be used whenever. Here comes in handy tools such as Ansible and Terraform, which have an easy to learn, easy to read, close to human language and code. Our previous scripts, which ended up having several pages, might only take up a few lines in these. Even though Ansible and Terraform are both YAC tools, there are some key differences between them. This means that they have different use cases. I'll speak about these soon. As you can see from the slide, there are many YAC tools. Even though we could try using any of them to create similar solution, each of them were made for different purposes. Keeping this in mind, we can order them under 3 categories. Config management tools, Ansible, Puppet, and StallStack can go under this. Server templating tools such as Docker, Packer, Vagrant, and finally we have Terraform and CloudFormation as infrastructure provisioning tools. I'll go into detail about them shortly. Config management tools are generally used for installing and managing software on existing infrastructure resources. Unlike the ad hoc shell scripts, these tools have a consistent and standard code, and this facilitates managing and updating their scripts. They're also created for running on multiple resources in the same time. An Ansible playbook can be uploaded in a repository such as GitHub or GitLab, which allows us to redistribute and reuse it as per our needs. However, the most important characteristic of this category is their idempotency. This translates to multiple runs of the code, and during these runs, the tools will only make the necessary changes to the needed components. Anything that already exists and is not included will be left untouched, without us having to interfere or to write more code. Let us have a look over the server templating ones. They're used for creating personalized images for virtual machines or containers. These images should already contain all the software and dependencies needed, which means that when we are ready to launch an instance, we'll have shortened the time for configuration and installation. Some of the most known examples are those offered by osboxes.org, the Docker images offered on Docker Hub, and other container registries. Those tools provide immutable infrastructures, unlike those mentioned in the previous category. Once our VM or container has been created, it is with the purpose of keeping consistency. If we need some changes though, we'll have to rebuild the image and relaunch the virtual machine or container. The last but not least category, the one which I'll focus this presentation on, is the infrastructure provisioning one. Infrastructure components can vary from servers, VMs, databases, VPCs, subnets, security groups, to storage spaces, and anything that is offered by our chosen cloud provider. CloudFormation is an example, but is dependent only on AWS infrastructure, not being able to cope and keep up with other providers. Terraform, however, is provider agnostic and allows via plugin support, and it's incredibly easy to assimilate documentation to use almost all cloud providers. So, why Terraform? Let's take it from the top. It's free, open source, it's created by a company named HashiCorp. It's easy to download and install, allowing us to create, maintain, and decommission infrastructure components in a matter of minutes. One of its most important characteristics is its ability to run on different cloud platforms, including both the public cloud, Google, Amazon, Microsoft to reiterate, and the private one at the same time. But how can Terraform do so many things in so many places at once? Well, through its provider plugins, which help and allow the users to access different external APIs. To understand how vastly the provider part is expanded, I'll just name a few of them. Just a few. On the cloud, we have GCP, AWS, Azure. On networking, we have BigIP, Cloudflare, Palo Alto. On the monitoring, we can use Datadog, Grafana, Wavefront. For the databases, we have MongoDB, MySQL, PostgreSQL. On the version control, GitHub, Bitbucket, or GitLab. The list goes on. The code we have to write for defining our necessity is HashiCorp Configuration Language, or HCL, a simple declarative language. Let's pause for a bit here. Imagine going from point A to point B, or better yet, from your house to downtown to grab a beer with some friends. Imagine the way: forward, left, right, up, down, a lot of way to go. That's the imperative approach. The declarative approach is when we call a rideshare service or taxi, provide the address to the driver, and he does all the rest to get us to our destination. Terraform is our driver in this case. So how does Terraform take our infrastructure to the destination? It has two main components, core and the before-mentioned providers. Through the providers, we gain connectivity to our desired platform. The core part is split into two input sources, the configuration part and the state part. The configuration part is where our code resides, the one we have to write for creating infrastructure components. In the second part, the state, Terraform retains the status of the infrastructure from the real world. Based on this, it determines the steps which are needed to follow and the actions so that our scope on the platform is precise. This state is a blueprint of the infrastructure created by Terraform. Terraform can also read the attributes of components from the real world if we have configured data sources. Terraform can also import other resources from the outside world, either manually created or by means of IAC tools under its control. It operates in 3 steps: init, plan, apply. If by any reason our infrastructure were to change, generally due to manual intervention, reapplying with Terraform will bring back our infrastructure to the before state. Any object under Terraform's care is called a resource. A resource can be a compute instance, a database on the cloud, or even a database on our local servers. When Terraform manages a resource, it takes care of its lifecycle from creation to launch up until its decommission. A personal note from a past experience which might have happened to you. Some time ago, when I was still learning to use a cloud provider's console for creating resources, I forgot a rather large compute instance running after work. Google offers us a free trial amount, about $300, which we can use for sandbox purposes. The other provider, however, did not have this option. With Terraform destroy command, we can easily avoid going to work at 2 a.m. in the night in order to turn off said forgotten instance in order to try to avoid any extra costs. And now let's go into detail about Terraform and its language. First off, any file that we want to have Terraform look at must have the .tf extension. HCL is composed from blocks and arguments. A block is defined between curly brackets and contains a set of instructions in a key value format which make up its configuration. In its simplest form, a block contains details about the platform on which the infrastructure resides, along with a set of needed resources on that platform. Let's take into consideration a very simple example where we want to create a simple text file on our local machine. In order to create this file, we have a block defined like this. Inside it, we specify the path of the file we want to create alongside the contents of this file using the arguments. The first element in this block is the resource. The second element is the resource's type, which is a fixed value and depends on our chosen provider. In our case, we can see that the type is local file. The type of the resource provides us with 2 valuable details. The first is the provider, and the second is the resource itself. The last part of this block is the name of our resource. This is a value internally interpreted by Terraform to keep track. This is of our own choosing, and since our file contains info about pets, I decided to name it pet. Between the curly brackets, we have the key value information. These are tied to the type of our resource. The first argument is file name, where we provide the internal path, and the second is what our file contains. File name and content are specific to our resource and can be changed. In other words, for choosing local file, it obligates us to have file name and content as parameters. And now, the boring part. We'll have to know a bit of theory to understand the example from the end of this presentation. I'll try to be as quick as possible. I'll speak about the 3 phases in which Terraform operates, about the state file and what that is, and how we can work together using Terraform. The first phase is the init phase. During this, Terraform downloads the necessary plugins for attempting connection to the providers. During the plan phase, Terraform will refresh the state file from the memory. The first time we run this, there is no such file. This means for Terraform that there are no current resources under its control, and it will go ahead and create a plan. When running the Terraform apply command, it will try recreating the plan and refreshing the state. It will reach the conclusion that there's no such thing for now and proceed to take us to our destination once we confirm by entering yes. Once created, our resources will have an assigned unique ID. What do you think will happen if we run apply again? Terraform knows that the resources are created and it doesn't do anything extra. But how does it know? We'll notice that there's a new file called Terraform.tfstate file in our project. This file is not created until the Terraform import or Terraform apply command is run at least once in a new project. It's a JSON file which maps the real-world resources to the resources defined in our config files. It contains every detail about them and consider it a single source of truth. If we change anything in our configuration, it will refresh the plan and compare it with whatever we have in the state file. There are a few things that we need to take into consideration when working with Terraform and this tfstate file, which is a non-optional feature. This JSON file stores data in plain text format, and when creating a larger infrastructure, it can and will store data about passwords, access accounts, IPs, info about the operation systems and images, etc. As you realize by now, we're talking about sensitive data, which means its security is vital. Google Cloud Storage is an ideal place, but of course there are other locations depending on the chosen provider. Being an automatically generated file, it's not indicated that to change it manually, because we might make mistakes and put in danger the whole infrastructure's integrity. If we absolutely need to change it, we can use a couple of Terraform commands to do so. Let's speak about teamwork. Knowing that the devs must work together as a team and our file is created on a local machine in our project, I'll try to explain how we can avoid some obvious conflicts on our infrastructure. Short imagination exercise. Suppose we have two engineers working together to create a compute instance in Google Cloud. After Adrian finished configuring, goes through the three phases of Terraform, he uploads the tfstate file in GitHub. Andre, the second engineer, pulls the changes, grabs the state file, makes the necessary changes in the configuration, goes through the three phases again, and uploads it back to Git. Looks okay so far, right? Well, in theory only. If both engineers work at the same time, there's a high chance that Adrian forgets to pull and is now working with an old version of the state file. There's also a chance that both developers try uploading the file to GitHub at the same time. Both variants may have damaging consequences on our infrastructure. We'll leave aside repos such as GitHub or GitLab because I've mentioned previously that our tfstate is in plain text. So how does Terraform help us collaborate? How does Andre's work remain undamaged by Adrian? On our local machine, if we try running Terraform apply from two different console windows at the same time, we'll notice that Terraform protects itself by creating a state lock and a file lock. It's one of the most important features by which Terraform stops us from corrupting the tfstate file. So how can we keep it safe while keeping in mind that people can work simultaneously on it? Terraform has a feature called remote backend, which we need to implement in our config files. Once configured, Terraform will, on its own, pull the state file while applying, make the changes, and automatically upload it back once done. Obviously, Google Cloud Storage and the other options have also the state lock incorporated as well. Well, that's about the code and functioning ways. Since we're nearing the end of this presentation, I'd like to thank you all for your attention and remind you the most important ideas you'll have to carry home. The times we live in are very changing, and thus the ability to adapt our products must be quick and easy to do. If someone asks you, no matter your field of expertise, well, maybe except the transport areas, if you need anything for your infrastructure, the answer is Terraform. After the short while when you start using and mastering Terraform's capabilities, do remember to keep the tfstate file safe. These being said, we can move on to the short demo, but before that, some questions. Okay. Yeah.
When you use Google Cloud AVS. Sorry, I have a question regarding the state file.
Yeah.
When you use Google Cloud AVS, you keep it in the
Yeah.
S3 bucket or somewhere because it has a provider for keeping the state in the cloud. But what happens if you use VMware Proxmox or some other providers that do not provide
well, that's
how from your experience? How would you choose to keep the TF state?
If we're working in a large infrastructure, this thing is a no-no. So
not alone.
Okay, so this is a very niche case, what you're talking about, and I just actually secure it. I don't know, encrypt it some way, keep it safe, keep it on, I don't know, offline after I'm done configuring it. But this will make a bit more, let's say,
you have
difficult
QA, for example. You want to provide a QA example for testing and something like that, and you will not use the cloud. You will create the infrastructure in your own cloud.
Well, that's not for the QA's eyes. That's literally for the developers or DevOps eyes only. The Terraform.tfstate file shouldn't be modified by hand, and QAs shouldn't. Okay, yeah, QAs shouldn't modify it. So since you've created the infrastructure already, that's in place. That's there.
Yeah, you are actually alone. You apply the state, and you have another colleague that needs to apply the state. From your experience, how would you keep the file not safe, but in order to both of you to work on this?
That's quite different. From my experience, I've never encountered this situation. No.
Okay.
So I've always used the remote backend, and when working offline, I told you I'd just keep it on a stick, like private stick that I use on my own. But if you need to collaborate with a different colleague, just, I don't know. It's quite difficult not to use the remote backend.
I thought from the experience, because this was one niche using other providers.
Yeah, it's quite difficult. So it's used mostly for working like on a large infrastructure, or you know, if you want to play around with it and explore it, then it's your personal choice where you keep it safe and secure. So if you want to break it, you can break it. You can start over, but that's your personal environment.
I know that it also provides a backend for Postgres to keep the state in a Postgres URL. Have you
provides
used
a backend for everything. There's over 100 providers.
No, to keep the state, just the state.
Yeah, it does provide that. But again, there are so many providers, and the documentation is so...
One question. When not using Google Cloud or AWS?
Yeah, no problem. Okay, back to the demo now. So,
do we have any more questions? Or you can start the demo? Start the demo.
Okay, so let's say one of our colleagues goes back to the early ages and wants us... Sorry?
Louder.
Okay, sorry. Can you please share the screen? Yeah. Not this one, the other one. The other one? There's a browser open. E celălalt ecran, dacă e nevoie. Este o fereastră de Google deschisă. So, okay, how can I share my screen then? Nu știu. Deci, display settings. Ok. Poftim? Да. Да, вырок. Okay, back to the subject at hand. So, let's say one day a colleague of ours comes and asks us for a new virtual machine. Nothing easier than this. We navigate to our favorite cloud provider's console. We go to the compute engine part, VM instances, and hit create an instance. Okay, we're going to keep the name instance 1. We're going to modify the region to Europe North 1, keep the zone 1 North A. We can see that a monthly estimate for this is $28, so that's a monthly estimate. We're going to downsize it to an E2 micro. We can see now that the cost is even lower. We're going to keep the boot disk as a Debian, and we're going to be using a service account which I've previously created. We're going to click create, and then the cloud provider does its job, and our instance is almost running. Okay, so everybody's happy, our friend is happy, and now has another request for us. He comes the next day saying that he needs 11 of these instances, but not in this zone. And yeah, for the cost diminishing, we need to remove this instance. You do imagine now that by using the console, it will take us a lot more time. So let's see how we can use Terraform to aid us in our quest. So the first things first, these are the files that we need. As we can see, they have the .tf extension here, and this is our service account key. We have defined in our providers.tf our provider Google with the credentials file, this one, from the project, this one. So we can see the project's ID from here. We can see how we can configure provider from the Terraform registry, which again is super easy to use, and we can see everything we ever need here. Good. So let's go through the steps of Terraform. First, we're going to need the Terraform init, where we can actually see that it's initializing and it has successfully been initialized, which means that we're ready to go. Now, let's see how we can import our manually created instance under Terraform's control. For this, we're going to need an empty block. I'm just going to decomment this. The rest are all comments. A resource block named Google Compute Instance, which we can see here that is what Terraform has in its registry. And I've named this manually created instance. Okay. Now, let's import our instance from the cloud under Terraform's control. The import command uses the type of the resource, the name of said resources, the project ID, the zone where our instance resides, and the name on the cloud. Once we've formed this command, we can copy it, paste it here, and let's see what Terraform does. Good. Import successful. We can now see the Terraform.tfstate file being initialized, and it appeared here. As said before, it contains every detail. Well, let's see how we can get rid of this instance faster. Okay, so in order to do a Terraform destroy, we're going to need some parameters, some mandatory parameters which we're going to take from Terraform's documentation. As we can see here, boot disk is required, machine type is required, name is required, and network interface is required. I happen to have these parameters here just for the ease of the demo. I'm just going to uncomment this and run a Terraform destroy. We can now see that it's asking us for a prompt. We confirm this value. Its plan is to destroy one resource, and we can see in our cloud provider's console that Terraform has already started working on our task, and its status is in stopping state. Good. Let's see how we can go to the second part of our colleague's request. Well, he mentioned we need to create another 11 instances. What can we do to make it in an iterative fashion? Well, Terraform has a count parameter here, which we'll set to 11. And by using this counts index, which starts at 0, we can name the instances. I'm going to uncomment this, save this, and wait for our instance to stop on Google. Okay, our instance is stopped. Destroy complete. Terraform acknowledges. And now let's go through the phases. Terraform plan. We can now see it plans to add 11 instances, 0 to change, 0 to destroy. We're going to do a Terraform apply, because we agree with the plan. Terraform apply. And we're going to acknowledge this. As we can see now in our cloud provider window, we can see that the task has begun. As mentioned, the index of the count will start from 0 and will go up to 10. Okay, so a quick note for the commands destroy and plan. So initially, when we ran the destroy command, we were destroying everything that the state file had in it. So what happens if we have a larger infrastructure and we only want to destroy just some components of that infrastructure? Well, it's easy. We could remove the entire block from our code, or in our case, let's say a friend doesn't need all the 11 instances and needs only 8. We can just do a Terraform plan. And now we can see that its plan is to destroy 3 instances. With the Terraform apply and confirming the plan, we'll see that he'll start to destroy these instances. And that's it about our demo. Hope you had a great time. And for more technical details, I'll be waiting at the Endava stand. Have a great day.